Okay, welcome to the fourth note set in our Unit 5 on analog to digital converters and DACs, but I think we're done with DACs. The last two note sets were pretty heavy theoretical stuff, having nothing specifically to do with audio. But we're now going to apply all that probability theory and random process theory to characterizing the noise from quantization. So if you remember back in the very first note set of this unit, we argued that a good way to model the effect of the A to D converter's quantization is through an additive noise. And we stated some assumptions there, and we said, well, we are going to have to kind of address more theoretically whether those assumptions are valid, or more precisely, when are they valid? And so that's what we're going to do in this note set. We're going to apply a lot of that probability theory stuff. So I've given you a couple readings here. There's stuff in the DASP book by Zolzer. So I'm going to be following that pretty closely, along with some stuff from a very nice paper in the Journal of Audio Engineering Society by Lipschitz, Wanamaker, and Vanderkooy. Very big names in digital audio. And I have a quote at the bottom here from that paper to just show how important people think this topic is. They state it's among the most frequently discussed topics in audio signal processing. So as I was saying in an earlier video, if you screw up in your A to D converter, it doesn't matter how good the rest of your audio processing is, your system will be poor quality. So it's that important. So let's get into this. Just reiterating some things that we talked about back in the first note set of this unit, talking about the ideal quantization operation. So we saw there that it's really just a mapping of an interval of real numbers into a discrete set of numbers. So the input can take on any value over a range. So from a minimum negative value all the way up to a maximum positive value. And inside our computer, we can represent those values only on a finite set of numbers. That's this discrete set of numbers. So that's the idea. We defined the ADC resolution or step size. Now, back in that earlier note set, I used a delta for that. I'm going to switch to Q here because that's what Zolzer uses in his book, whereas most other people use a delta. And I'm going to base most of these notes on the stuff in the DASP book. But I will also be using some results from other places. Maybe not so much in this note set, but in other note sets. And in the first note set, I used delta. So we are going to have to switch between them, and I'm sorry for that, but this is something that you need to learn how to do. Don't get tied into a specific symbol for a concept. Think about the concept and be able to draw from resources that may use different symbols for that. So for right now, Q will be the resolution or step size. It's the same thing that we had a delta for earlier. So here's a picture from the DASP book, and that's showing the operation of this quantizer here. So remember, this is after we've already sampled and held, and we're now going to quantize that sampled value into a binary word that can be stored, and that becomes one of the samples. And so the X value can take any value along this axis, and this is showing what the output value would be. So if for example, x takes on this value, it's going to be represented by q. And I wish Zulzer had the x boundaries listed here, but this is q over 2 and this is 3q over 2. So q is right in the middle. So if you have a value that's just a little bit below q, it gets rounded up to q. So this quantization mathematically can be thought of as a rounding operation, as we saw before. Now, we don't normally do this in our audio processing, but to get an idea of what that error looks like, that's what we're interested in, is characterizing the error that occurs when you do this quantization. So again, if you just run x along the values that it's allowed to take, you see that you get this kind of zigzag thing. And the largest it can be is q over 2, and the smallest is negative q over 2. So that's pretty obvious. Now, we had talked about this ideal quantization noise model. So we have that noise, which I called E of n, and Zulzer called E of n on the previous slide. We want to characterize that noise to understand how it's going to affect the quality of our audio. Here's physically what we have, and we're going to model that this way. This is what we talked about before. We imagine that error E of n that occurs when we do this quantization, we think of it as just an additive value that we add to q of n to create the output. So mathematically that's equivalent. The difference is, how do we get this E of n? Well, when we're again, we're not really implementing it this way. So when I say how do we get that, I really mean how do we characterize it. So how do we characterize this E of n is an important aspect of modeling the effect of the quantizer. So we stated the last time, or at the very first note set of this unit, we said model this with some probabilistic characteristics. So we assumed, and I've got that underlined in bold and italic, we assumed that the error is uniformly distributed. Now we saw over here that when we just run x linearly through its values, it does stay between minus q over 2 and q over 2. So we do know that it's limited in there, but we don't necessarily know that all those values are equally likely. But we're going to assume that. So we say the error, this E of n, is uniformly distributed. Aha, so now we have a probabilistic model for that. We can talk about how much power is that adding. We can talk about how is that power spread over the frequency domain. That's the power spectral density point of view. We can ask, how is that noise correlated from sample to sample? We can even ask, how is that noise correlated with the signal? So these are all questions that we can ask and answer because they help us understand the impact of actual quantization. We can predict what it's going to sound like, how bad it's going to make the audio sound and things like that. So here's the form that we talked about, the rectangular function. Just gives us a PDF that looks like that. And we also showed finding the variance of this. Well, clearly it's zero mean. We can see that just by looking at the picture of the PDF. But we find the variance of that, and it's q squared over 12. Well, okay, last time we had delta squared over 12. Same thing, just a different symbol. Another assumption we stated back in note set 1 of this unit was that the noise is uncorrelated from sample to sample. In other words, it's white noise. And I said that as if it were on a fortune cookie. The error then does not affect the error now. So we know that means that the random process view that we're using to think about that noise, E of n, we model it as a white noise. So its power spectral density is flat. So its power is spread uniformly over the region of frequencies that we're dealing with. The other thing that we assume is that the error is uncorrelated with the signal. So that's kind of interesting. And that's maybe the hardest one to accept here, because clearly the value that we get here and the error value that links those two things together depends on the value of x, right? If it's just a little bit closer to a quantization level, the error will get smaller. So this one seems a little bit far-fetched, but we'll see that it's actually not that bad of an assumption. So these are assumptions at this point. We need to explore these assumptions to, first of all, verify that, yeah, they do kind of make sense. And can we nail down some fairly concrete conditions that we can say, if this is true, then these assumptions will be true? Or even better, when this occurs, in these kinds of scenarios, these assumptions fail. That would be a good thing to know. And then we try to avoid or mitigate those scenarios. Now, these assumptions have been around for quite a while. They were first published by a very famous DSP researcher named Bernie Widrow back in 1961. And in fact, Bernie Widrow now has an entire book out on the theory of quantization. So if you're really interested in this stuff, that's probably a good book to track down and read. Now, just as an illustration, we're going to show that this model does not hold in a certain scenario. So that will tell us that we really do need to explore this more deeply. Now, there are scenarios where this model does hold. In fact, I showed an example where I had 3 sinusoids that were quantized, and the noise floor looked nice and flat. So in that case, we seem to have shown at least some of those, that the noise looks like white noise. But let's take a look at this. This comes right out of the paper from Lipschitz, Wanamaker, and Vanderkoy. So they start with a sinusoid. And look, the way they list the level values here is kind of interesting. It's a very important way to think about it. They're representing it in terms of LSB, least significant bit. So that's the value of when the lowest bit place is just toggling up and down, and with a sign bit out in front to go to the negative. So that's really Q and minus Q. But it doesn't matter how big Q is, and it doesn't matter how big the sinusoid is. It matters how big the sinusoid is relative to Q. So we're saying that this amplitude is 2Q, whatever Q is. It doesn't really matter. So the peak is 2 LSBs. It goes down to minus 2 LSBs. So it is a 4 LSB peak to peak level sine wave, and it has a frequency of 1 kilohertz. We're looking at 1 cycle over 1 millisecond. And it's not terribly important here, but this was probably sampled at something like 44,100 samples per second. So this is where we start. That's the signal that goes into the quantizer. And so now this thing is going to get quantized. Anything that's below Q over 2 is going to get quantized down there. Then it's going to get quantized to the 1 level and the 2 level, and so forth. And you can see that happening here. So quantized to 0, quantized to Q, 2Q, 1Q, 0, minus Q, and so on. Now, look at that. That does not look like a sine wave that's had uniform white noise added to it. If that were the case, this result would look like this with just a nice, noisy, uniform distribution around it. It'd be more fuzzy than that. The up and downs would be much faster. But that doesn't look like that. And in fact, if we subtract off, if we look at the difference between these two to get the error signal, again, shown on an LSB scale, we can see several things. One, it does not look white, and we see remnants of the actual signal structure here. So it looks like it is not uncorrelated with the signal. And now we take a DFT-based estimate of the power spectral density. There's a lot of ways to do that. I can't remember the details of what they did, but whatever they did is going to be similar to something called the Welch version or method for estimating the power spectral density. In fact, they may have used that. I can't really remember. It's not important to this discussion, but they basically used DFT-based signal processing with some cleverness to make an estimate of the power spectral density. Now, what we would expect is a spike at 1 kilohertz from the sine, and if our model were correct, we would see, and this, I should point out, this is dB relative to the level that the theory predicts the power spectral density to be at. I provide a little bit more detail about that later. So we would expect a nice flat power spectral density at that level where they put a dashed line. But we see, in fact, it's not. We get all these spikes, all these spurs. Now, we talked about spurs before when we said, oh, they're, nonlinearities and jitter and so forth can cause spurs. That's not what this is. That's not what this is here. These spurs are from the fact that an ideal A to D converter with a quantizer still has these spurs. It doesn't behave according to our assumptions. So something is wrong here. And I'll give you a hint. The problem is it's a very low amplitude sinusoid, only 2 LSB, right? So if this were like a 16-bit A to D converter, this thing is very, very small level sinusoid going into it. So one thing we're seeing is maybe, and this turns out to be true, maybe our assumptions don't hold when the signal is low amplitude. We saw a previous example where it looked like the assumptions did hold. That was back in the first note set, kind of alluded to it, where we saw 3 sinusoids, one of which was at full scale. And there things looked more likely to adhere to our assumptions. And so that's actually where we're going. But we'd like to put some theoretical power behind this so that we can really know what's going on. So we're going to start off with what's called a first order characterization. First order probabilistic characterization of the quantizer output. So there's 2 important things here. First order and the fact that we're looking directly at the output, not the error, just the output. So by first order, we mean things that are assessing a single random variable in the stream of the output random variables or the output process. So the PDF at a given instant of time, the mean, that's first order, right? Expected value of well, we'll call the output y or x sub q, expected value of x sub q, the variance, single random variable. So a single output sample, that's the thing that's important here. After we get through this, we'll go look at joint PDFs. That will be second order because we'll be looking at what's the joint PDF between the output process at this point and some other point. And that will also lead us to autocorrelation function, which is a second order thing, right? Expected value of the process at n and n plus k. Okay, so, all right, so we've now switched to X and Y being the input and output. And here's our quantizer. And we've just said, okay, assume that random variable goes in with a PDF. And look, we no longer have to think about this as a stream of random variables. We can just do it instant by instant and say, at this instant, assume this is the PDF. And if it's wide and stationary, that PDF will be the same everywhere, but irrelevant to this discussion. And then the output Y, and our job here is to try to understand what that is. So that will depend, obviously, on the input PDF and on what the quantizer does to the input signal. Okay, so the input is a continuous random variable. So that does clearly have a PDF. Now the output is actually a discrete random variable, right? Because it can take on only a finite set of discrete values. So discrete random variable, yet I'm talking about a PDF. Well, a couple note sets ago, I showed you how we can press into service a PDF to characterize a discrete random variable. We just need to use delta functions. So we can describe the PDF of this using delta functions. And so here's a nice picture. This is something I took from Zolzer's book, but I modified it because Zolzer didn't show these with arrows on them. So they did not look like delta functions. I think he just had little dots up at the top. So I replaced all those dots with arrowheads so that we can clearly see that these are indeed delta functions. And so here's what's happening. We can say here's this curve here is the PDF of the input. And these deltas here are the PDF of the output. And we can see that the output can only have values that take on values of 0, Q, minus Q, 2Q, minus 2Q, etc. That's why the deltas are centered there. And so if we think about it, the probability of that should be captured here really should be the area in that cell. I didn't do a very good job up at the top there. All of that probability gets concentrated into this value. That's kind of how that works. And we'll use that in our analysis, that kind of view. All right. And in fact, here's how we write that out. So we can describe this PDF of Y this way. For Y lying between minus Q over 2 to Q over 2, we have a delta function centered at 0, and the value that gets multiplied by that is just the probability that X gets quantized to the 0 level. So the probability that X lies in that region. And then similarly, we have another delta function that's out at plus Q, and the area that gets assigned to that is the probability that X lies between these two limits, and so on, and so on, and so on. So that's a pretty cumbersome way to write it. And in fact, if we look at this delta function, we don't really need to limit it to only that range. Outside of that range, the delta function is 0. In fact, even with inside that range, the only place the delta function is non-zero is at y equal to 0. So really, we could just add all of these things together, and they won't interfere with each other. Where any one of them pops up, all the others are 0. So that's what we do here. And we just do a little bit of manipulation of symbology. So instead of having to write out all these integrals, we're just going to say, let's write those integrals in terms of some function, which we'll write as w of qk, or kq. So you can see that's what these integrals are up there. So I'm just replacing these integrals with that symbology. What is that? Well, that is the probability that X gets quantized to the KQ level. So that's it. That's all we're talking about there. And again, here's that picture from the previous page, just modified again with some arrows pointing out. So the delta functions are this expression. Their heights, remember, graphically are shown to represent whatever number is being multiplied by them. Technically, delta functions go to infinity, but when we show them on a plot, we tend to have their graphical height reflect the number that's multiplying by them. That's technically changing the area of the delta function. Okay, so we've got a nice little representation here, and remember this WKQ is the area of this underneath the input PDF. Okay, so let's continue on. A lot of this is just tidying things up and rewriting them in a little more convenient form. And that's all we're going to do here. So we wrote our W of KQ this way. Let's rewrite that this way. So instead of KQ, we're going to define something here on a continuum. And all that is this rectangle function sliding along here. And so if we were to replace the y here by KQ, we would get the y replaced by KQ. So that just slides the rectangle into the right position. So going back here, we're just sliding a rectangle so that it hits the right position here. And we'll multiply and isolate that little section. So that's what we're doing. And then we integrate that to get the area. Well, if we don't do it at KQ, we can do this a little bit more elegantly. We can interpret this thing to be a convolution. So we can write rectangle convolved with the input PDF. So that's going to give us a function on a continuum, and then we just need sampled values of that. So that's perfectly okay. So if we define wy this way and then just take specific values out of that, we're good. Now, let's also look at the delta functions. If we go back here, we see we've got these delta functions here. And if you think about it, we can pull this out in front, right? There's no, nope, not quite yet. I'm not quite there yet. Let's introduce just this stream of delta functions. And we'll see how that comes into play in just a second. So it's just a bunch of delta functions spaced by q. So on the y-axis, here's the y-axis, we're going to have a bunch of delta functions spaced by capital Q. Remember, Q is our quantizer step size. So Q, 2Q, minus Q, minus 2Q, etc., etc. Okay, so that's what this thing looks like. And we'll just assign a nice simple symbol to that, delta sub Q. The delta tells us we're talking about deltas, and the sub Q reminds us, oh, it's a stream of them spaced every Q. Now, here's our previous form that we wrote out on the previous page. We've got this thing inside where the K is operating on it. But here's the cool thing that we can do. We can actually pull this thing out in front and rewrite it as W of Y times this. Because once we have this W of Y, when we pass it through here, we would end up with W of Y for each term times a delta of Y minus KQ. But since this thing is non-zero only when Y is equal to KQ, when we pull that inside, we can replace that by KQ and we get the right form. So that's a characterization of delta functions that you should have seen in a signals and systems class. And at that point, you might have said, I don't know why the professor seems to think this is an important thing. Doesn't really seem that big to me. Well, it just pops up every once in a while. All right, so now we've got this thing pulled out in front, and this is what we already defined. So we can now write the W times the stream. So the stream is there, and now we're saying, oh, what was W of Y? This convolution. So look at that. I've got that in a big red box. That's going to be something that will be important for us in just a little bit. And in fact, it's a key result. This links the input PDF to the output PDF. So that really characterizes everything from a first order point of view, first order probability analysis. This tells us everything we need to know. You tell me what the PDF of the input looks like. You tell me what the Q is, and I can tell you what that probability density function looks like. Then we can find things like, what is the mean? What is the variance? Et cetera, et cetera. Okay, so, but here's the problem. We have that written out in terms of convolution. And convolution is hard to think about, right? If I show you a shape for this, can you imagine just off the top of your head what the convolution of that with this rectangle looks like? Probably not easy to do. So remember characteristic functions. We introduced those 2 note sets ago when we studied probability theory results that we needed. And they were a Fourier-based thing. So it's really essentially the Fourier transform of the PDF. So if we take a PDF result and convert it into characteristic function result, anything that was a convolution in that result is going to get converted to multiplication. We know that's what Fourier does for us. And anything that was a multiplication is going to get converted to convolution. So those are 2 Fourier transform properties that you should have seen before. So here's where we started. That's our big result that we saw on the previous slide. And there's a multiplication in there, and there's a convolution in there. So I actually have both of these in there. So the convolution is going to become a multiplication, and the multiplication is going to become a convolution. So if I take the Fourier transform of this side to get this characteristic function, I'm going to apply these properties. Now, just a little note along the way here. Sulzer defines things one way, and Lipschitz, Van der Kooi, and Wanamaker, I just shortened it to just Lipschitz. Lipschitz et al. Use a different notation, so for the characteristic function. So remember, when I introduced the characteristic function, I pointed out, it looks like a Fourier transform except with a plus in the e to the j term. Well, Lipschitz doesn't do that. Lipschitz and his co-authors use a negative j there, so slightly different. And also notice that Sulzer's u value there is just by itself, whereas Lipschitz uses a 2 pi u. That's the difference between, in regular signal Fourier transforms, using an f, that would be Lipschitz view, versus an omega, that's the Sulzer view. So that's the difference. So all that's going to happen is this. If you try to compare results in Lipschitz paper to Sulzer's book, there will be sign flips here and there, and there will be 2 pi's in one that aren't in the other one. But other than that, everything else is the same, but I'm going to use the Sulzer form for right now. So if we do that, I take the Fourier transform of this, and I get the characteristic function. Now I want to take the Fourier transform of all of this, but I'm going to use some properties, right? I'm going to use the property that multiplication is going to go to convolution, and convolution is going to go to multiplication. But before I can do that, I need to know what is the Fourier transform of this thing. Remember, that was a stream of delta functions, right? So let's back up here. That thing looked like this. Just unit area delta functions spaced by q. So the spacing between these is q. Okay? So what is the Fourier transform of that? So the Fourier transform of that, here is that thing. Double arrow means take the Fourier transform. If you work through this, you can show that it itself is a bunch of delta functions. Yeah, there's a number out in front, but that's the least important and interesting part of this. It's delta functions spaced by something defined to be u0. What's u0? It's 1 over, or well, it's 2 pi over q. Aha. So let's back up here and just show a picture here. So the delta q of y has delta functions that are spaced like this. Dot, 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 q, 2q, 3q, and so on. So the spacing is q, and it transforms to this thing. Another stream of delta functions. And what was the spacing of those? They were spaced every u sub 0, which was 2 pi over q. So the spacing here is 2 pi over q. Spacing here is 2 pi over q. Here's the key thing. Spacing here is q. Spacing here is inversely related to q. So if I decrease the spacing here, I'm going to increase the spacing here. That's a key idea. So that's kind of interesting. A stream of delta functions transforms to a stream of delta functions. Yeah, there ends up sometimes being some constant out in front. The spacing in the original domain is inversely proportional to the spacing in the transform domain. That's the key thing. So as the spikes get closer here, that's what I get when I go to finer quantization. I will get spikes here farther apart. Keep this in mind. Should have put that in red because that's a key insight point here. Okay, let's move on. So here's my output PDF. I'm now ready to transform it. I've got all the results that I need. This multiplication is going to change to convolution, and this convolution is going to change to multiplication. I know what the Fourier transform of that is. I know what the Fourier transform of that is. That's right off from a Fourier transform pair table. It's going to be a sinc function. And I know at least symbolically the Fourier transform of that. It's going to be the characteristic function of the input. Okay, so here we have it. This thing transforms to the delta function spaced every u0. Remember, u0 is 2 pi over q. There's the sinc function that comes from there. There's the characteristic function of the input. And here's this multiplication being converted to convolution, and here's this convolution being converted to multiplication. Nice. Really shows the power of Fourier transform analysis. Now what am I doing? Well, I'm just manipulating some stuff here. I've got a 1 over 2 pi times u0 times q. Remember, u0 and q are inversely related to each other. So this was 2 pi over q. That's going to cancel. That q in the denominator will cancel with that. Leaves me with 2 pi over 2 pi. So all of that multiplies to be equal to 1. So that's why these things don't show up down here. But everything else stays. I've got that. I've got the sinc function without the q because that got canceled. I have the characteristic function. But look, there's a convolution. I used a more standard symbol than what Zolzer used here as the star. So crap, I still have a convolution. I thought this was supposed to fix that for me. I made this big deal about how convolution is hard to see, so we want to get rid of it. And we did get rid of this one, but we got another one. But don't worry. This convolution is easy. We're going to use the properties of deltas and the sifting property of deltas. So when you convolve something with a delta, single delta, it just replicates the thing moved to wherever the delta function was. So it's going to take this thing and just plop it down at the location where this thing was. So all it does is just replaces these arguments here by these quantities. So that's what we have going on here. So now we have a sum. Look, no convolution, just a bunch of terms, a sum of a bunch of terms, and each term is a product. So it's not exactly what we're talking about, but it's kind of like this is a Fourier transform or a spectrum of a signal, and this is a frequency response of a system. It's not really what we're doing, but it's analogous to that. So this is something that we're looking at if we have that, and this is something that happens to it to make this. So we can look at how each of these terms ends up behaving and interacting with this. So all this is just the characteristic function shifted by some integer multiple of omega 0. And I should point out that Zolzer sticks j's in the argument of characteristic functions. And back a couple note sets, I warned you that some people do that. Well, Zolzer is one of those. So I've just repeated that result just so that we can see it sitting there while we do some more thinking about it. So here's an interesting illustration that shows us what's going on. So here's my input PDF. Here's the input characteristic function. So that's the thing that's going to show up there, but it's going to get shifted by certain amounts. So remember, a broad thing here, its transform is going to be narrow. So a broad PDF, so in other words, PDFs that have large variance is going to give us small value of B here. And what is that B? I mean, I'm just alluding to the idea that the CF is, quote unquote, band limited. It's not really going to be band limited per se, but we can think that way. Okay, so then what happens, right? We saw that our PDF of the output has all of these delta functions, and we just showed that the characteristic function of the output is this thing shifted to different positions multiplied by a sinc function. So we can see this thing gets shifted to different positions. Now, it's a little hard. I didn't show a lot of the effect of the sinc function, but that's on every term. So this first term here, set k equal to 0. So it's our original times this sinc function. Now that sinc function might do something like this, right? Yeah, we can work out exactly what it does. But my point is that over the range of the characteristic function of x, maybe that sinc function doesn't drop down very much. So that's why this thing looks pretty much like that. But there is some effect. And then this thing out here is just for k equal to 1. So it just takes this thing and shifts it out to be centered there and takes a sinc function and puts it on top of it. That's the idea. Okay, so this is a pretty good result. It allows us to see some pretty neat insight. And we would never be able to get that insight by looking at this. That's the beauty of characteristic functions, same beauty as looking at signal spectra. So this is actually remarkably similar to sampling theory. It's not sampling theory, but the mathematics looks a lot like it. We end up with spectral replicas of the original. Now there is a sinc function involved, okay? So this actually looks a lot like spectral replicas with a sample and hold. Very, very similar to that, actually. So the thing is if, again, I'm not saying that we can get a perfectly band-limited characteristic function. We'll revisit those things. But if, say, the characteristic function were band-limited, then we could make sure that we decrease Q enough so that these things are pushed far enough out so they don't overlap. That's kind of interesting. So that's a good insight. And that's what happens as we reduce the quantization spacing. Now, Shannon was interested in reconstructing the signal from its samples. We're kind of getting samples of this to provide this, but we're not really interested in trying to recover the PDF. We're interested in what effect does it have in the sound of the actual signal. And we can characterize that by finding the moments of our output random variable. What do I mean by moments? We talked about that in our probability theory note set. I think it was note set 2 in this unit. So let's look at the k equal to 0 term in this. So this is the result that we just came up with. Let's just focus on the k equal to 0 term. So we're going to let that go away. We're going to let that go away. We're going to let that go away. And we're going to define the thing that's left. And then we're going to get rid of all the other terms. The thing that's left, that's right here. Just for convenience, we'll define that as g sub x as a function of u. And again, Zolzer just carries the j around there. So you can see that, yes, indeed, it depends on the characteristic function of the input. So let's just define that. And now it can be shown. So I had to limit how deep down into this we actually dive, because it's a full semester course, but this only takes up part of that semester. You could literally do an entire semester just talking about quantization results. And like I said, Bernie Widrow has an entire book on that. So it can be shown. Somebody has shown this. And I stated here as an if, but in reality it's an if and only if. But if we can look at this function and we find its mth derivative, evaluate that at k omega 0, if this thing is equal to 0 for all values of k that are not 0. So remember, this is we're not saying this, that we're looking at other terms here. We're fixing ourselves at one term, but then we're looking at how far out it goes, right? So let's go back to this picture here. We're really looking to see how far out, does this thing go? And we're looking at it in these positions right here. That's what we're looking at. But we're also looking at its various derivatives at that. So we want this to hold for m equal to 1 and 2. Look, it's not important whether you could actually ever do that. That's not what we're aiming at. You'd never be asked, or you shouldn't ever be asked, here's a input characteristic function, evaluate that. That's just busy work, really. But what does this tell us? If this is true, then we will see that the mean of the output is the same as the mean of the input. That's the important thing. The fact that it's equal 0 is just our assumption, which is typical for 0. So it's the equality of input-output mean that's important. And then the variance of the output is, if this is true, the variance is the variance of the input plus q squared over 12. That's the variance of our assumed white noise model, uniform PDF. Ha! So this does, in fact, look like it is supportive of our assumption, because if we add two independent random variables, the variance of the sum is the sum of their individual variances. So that's why I say this is supportive of our assumption. We haven't proved that it is independent, but we've proved that it acts as if the noise is independent of the input. That's kind of a nice result. And it has to have this condition held. Remember, that depends on the input characteristic function, which depends upon the input PDF. So being able to guarantee this for any old audio signal that you want to put in to your A to D converter, very, very hard to ensure. But we have a hunch that as the PDF stretches out, higher amplitudes that the input signal can hit, the variance will, that means a higher variance on that input signal. That means bigger peaks. So remember, that means that this thing gets broader, this thing gets narrower, and these things will be more likely to satisfy, or at least approximately be zero out at these positions. So that again matches nicely, or meshes nicely with what we've seen so far. Large amplitude sinusoids seem to be quantized in a way that followed essentially the assumptions that we made, but a low amplitude sinusoid did not. So low amplitude sinusoids, if we could think of it as having a PDF, would not satisfy that. Okay, so let's charge on. So that's our first insight to some theoretical results. They were first order characterizations of the output. Now let's go to second order characterizations of the output. So that means joint PDFs of pairs of samples. Autocorrelation function is second order. Power spectral density coming from autocorrelation function is a second order characterization. So here's the result that we just came up with. We have that already. And so now if we just follow similar arguments, I'm not going to go through all of the steps. They're literally exactly the same, except now we have two-dimensional functions. So we're taking two-dimensional Fourier transforms. It's the same. It looks exactly the same. You can Google two-dimensional Fourier transform and look at if you want, but the ideas carry over. So if we go through the similar kinds of things, we can convert, or we can arrive at something that looks like this, extended to a joint PDF. So instead of this delta Q, we have something that looks like this. And that's just the product of those two individual delta functions, streams. And we have this rectangle here is going to be the product of the two individual rectangles. And then we have the joint PDF of our input. And so that's the idea. So let me just draw some pictures here to show you what these things look like. What does this thing look like? It's deltas. Basically, this thing you have to imagine extends constant over the y2 variable, and this one extends constant over the y1 variable. So when they multiply each other, you end up getting, so if this is my y1 variable and this is my y2 variable, I'm going to put a bunch of dots here. That's on a grid with spacing of q. So here's hash marks on each axis. Those hash marks are spaced by q. So think of it as like a bed of nails. That's what this function looks like. A bed of nails. So that's what that thing looks like. A product of two rectangular functions. Again, here's y1, here's y2, and we're going to have a rectangle. So it'll be 1 over this region. So in here it'll be 1, and outside here it'll be 0. So that is a two-dimensional rectangle function. And so now we're going to use two-dimensional Fourier transform ideas following very similar steps. Again, I don't go through them all, but this multiplication turns to a convolution. This turns to a multiplication. We get this this thing transforms into another bed of nails kind of thing, and then sifting property with the convolution and so forth, and we get something that looks like that. Very, very similar. We've just got double arguments here. We've got a product of two sinc functions because we had this thing being a product to begin with. And so it just carries through very, very nicely. And similar to before, we define the k equal to 0, L equal to 0 term. So we get rid of this, we get rid of this, we get rid of that, 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 and look at that one term in this sum, and define that, same as before, to be a g sub x function. And you know what's coming next. A theorem that says it can be shown, and here I state explicitly here, if and only if, and now we're doing double partial derivatives along u1 and u2. Uh-oh, typo here. That argument should be this argument. So that should be fixed. Very, very similar ideas. Then we get, and look, this is consistent. This is supportive of our assumption of additive white independent uniform quantization noise. So we have results that show if you add together two independent processes, the resulting autocorrelation function is the sum of their individual autocorrelation functions. Well, this is the autocorrelation function of the input signal, and this is the autocorrelation function of a white error noise or white quantization noise. And likewise, transform this into the frequency domain, you get the power spectral density of the output, and you get the sum of the input PSD plus the power spectral density of the additive noise. The fact that this is a delta function and that this is flat tells us that this looks like white noise. The fact that they add to the signals characterizations supports that it is an independent, and we've already seen the characterizations of the PDF tell us that it should be thought of as uniform quantization noise. Although we'll have more to say about that in just a little bit. So it's less supportive here so far of the fact that the individual PDF is uniform, but very supportive of it being white and independent of the signal. So by independent, I mean independent of the signal, the input signal. So again, we have some pretty hairy conditions to check, but no one really ever needs to go through and check because no one ever really knows what the characteristic function of the input's going to be. But it does give us some insight into why does it work well here and not well here? Why, when I have a large amplitude input, things behave like I expect them to do, or behave as I assumed them to do. but when I go to a low input amplitude, it doesn't work. So we're starting to see why that is true. So that's all good. All right, so we did first order and second order characterization of the output. Now we're going to turn our attention to characterizing the error itself. Now we're going to first do a first order characterization of that. So I'm going to say, here's the input PDF. We talked about how the error basically ends up being contributed by all of these little slices. So if you wanted to know what is the probability that I'll get a certain error, you have to account for all the probabilities that the signal might lie in each one of those slices, and those all essentially sum up. It should be a weighted sum, but they should just sum up to give the PDF of the error. So this is all a graphical motivation. I can see that if I'm summing up these slices, this one dips when that one goes up, this one dips when that one goes up. So we can kind of think that those should all sum up to give something pretty flat. That's by no means an appropriate proof, but it's kind of a motivation that, yeah, maybe I'm going there. And then this is the mathematical result that really says what I get here. So it's this rectangle here is just sitting there around this position. I suppose I should draw it over here. And this part is just moving these different things into position to be multiplied by that rectangle and then adding them all up. But we've already seen, similar to things that we've done already, we can write the sum of these different things as a convolution. So that's just like what we did with some of our earlier analysis a few slides back. Similar kind of mathematical trick. So now we have a nice mathematical form for the error PDF. And we can now analyze this to see what needs to happen to make that a uniform PDF. Okay, so off into the characteristic function world. That's why we introduced those ideas. So here's what we just came up with on the previous slide. And now we're going to take a Fourier transform to get to the characteristic function. I'm doing Zulzer's form, so it's not quite a Fourier transform. It's with the plus j rather than the minus j. This product becomes a convolution. This convolution becomes a product. This thing transforms into another sequence of deltas. These deltas are spaced by q. These deltas are spaced by 2 pi over q. So inversely proportional spacing on those, just like we saw before. We've got a q over 2 pi and a 2 pi over q. So those all cancel out. And we end up having something like this. And again, we play that same trick that we did before. We have a function over a continuum multiplied by a bunch of delta functions. You can pull it inside and just write it at its sample values where the delta functions are. So again, that little trick shows up a lot. So now we have linearity of convolution. Let's look at this. Where is this a function of u? Not there. This thing inside here is only a function of u there. So we can pull this thing inside and just pull those out as coefficients. So it's going to be this thing convolved with each of these terms. Oh, but look, that's a convolution with a delta function. Very easy to do. So sifting property of the delta function says I get this thing replaced at k u0 or shifted to k u0. So the u here gets replaced by u minus k u0. Same thing down in the denominator. So there's our result. So this is the characteristic function of the error is equal to values coming out of the characteristic function of the input times each one of these sinc functions, and then add it up. So very similar to kinds of things that we've already seen. So I'm just repeating that. We just showed that this is the characteristic function of the error. And here's a theorem. Again, I'm not proving the theorem, but it's easy to see the if part anyway. But here it is. If and only if the input CF satisfies the following condition. So in other words, we're looking at this thing, right, at these points. That's what we're doing. So if the input characteristic function is 0 at all of these points, excluding k equal to 0, then all of the terms of this go away except the k equal to 0 case. And remember, every characteristic function evaluated at 0 is equal to 1. So then we're left with, if this is true, then this whole thing collapses to just the k equal to 0 term, and that is true. So we get just this without the k in there, and that's what we have there. So there is the characteristic function of the error if this condition is satisfied. Haha. Well, what does that transform back to? Inverse Fourier transform of that. Now again, the Fourier transform needed a plus j, so the inverse Fourier transform version of this needs a minus j. But the math all works out. Sinc function transforms to rectangular function. Interesting. That means it's uniform. So we now know precisely the if and only if conditions needed for the error to be uniform. We also know if and only conditions for the error to be independent and white. We've established those already. We're going to look at that a little bit more in detail still, but we've already essentially got very supportive results indicating those conditions are met. But let's do it this way to really nail it down. Second order characterization. So we need the joint PDF of the noise. And again, I'm going to go through these pretty quickly because it's just a 2D version of everything we just did for 1D. So using all the similar ideas, we get the 2D version of this here. We get a product of sinc functions along along each of the variables that we're talking about. And then the condition is the following. So that's just a 2D generalization of what we saw before. And in that case, all of the terms of this go away except for the k equal to 0 term. So, and again, this joint characteristic function at 0. So this gets replaced by 0 and 0. That goes to 1, and we're left with the sinc functions, but without the k in there. So what do we get? The joint characteristic function looks like this, a product of two sinc functions. And now we take the inverse 2D Fourier transform. So I'm just showing here that they form a pair. So I'm going backwards. But again, plus j for forward and minus j here for the inverse. And this is going to transform to a rectangle, and this is going to transform to a rectangle. And so what does that show us? The product, the joint PDF is a product of individual PDFs. So yeah, the noise is independent at any pair of instants. That means it's white. We've established that yet again, another way to see that. So we can capture everything we've seen by just stating, if this is true, then we get the following results. The autocorrelation function is that of a white noise. The power spectral density of the error is that of a white noise. So the noise is white. We've also seen some other conditions that show when the noise is independent of the signal. We saw that when we looked at the second order and first order characteristics of the output. So we've got conditions for all of the things that we want to ask about. So here's the summary. It's uniformly distributed if and only if that holds. It's white if and only if that holds. It's independent of the input if and only if that holds. And so what does that tell us? Not a lot. It gives us insight into what's going on in the mechanism. And it also shows us that those assumptions are not uniformly valid. Pun intended there, I suppose. There are times when they won't be met, and there are times when maybe they will be met. That's a big handful of things to ask of the input signal. How can we guarantee that audio that we're interested in recording and listening to is going to satisfy those? We can't. We cannot really guarantee that we'll be able to meet these conditions. So what good was all of this? You'll see soon enough in the next video. So we saw an example that said, oh, when you have small amplitude sine wave, things didn't work. We could also do, it doesn't have to be a sine. It's not about sine, it's about the small amplitude. We could generate a small amplitude random signal, put it in, and we'll see similar kinds of things. Does not satisfy these conditions. We wouldn't even have to check. We could just look to see in an experiment inside MATLAB. Does the noise behave the way our theory or our assumptions say we think it's going to behave? Nope, it won't. Not when it's small amplitude. So virtually all low-level signals will have a narrow PDF, which means we have a broad characteristic function. And all of these things are about the characteristic function not interfering with other terms. So the broad characteristic function means you can't really, means that the characteristic function as it gets shifted is going to be interfering with each other. Just like an aliasing kind of setting, okay? Remember, the math, the setting isn't the same as sampling, but the math is the same as sampling, and so we get a feeling for that. So when we have a narrow input PDF, we effectively have, quote unquote, some form of CF aliasing happening, and these conditions will not be met. So that's bad. So what can we do about this? Well, if you don't have any low-level signals, that's not a problem. But, you're going to have fade-outs at the ends of things, or maybe fade-ins, and maybe you'll have some quiet passages. Well, back in the compressor unit or note set, we saw that over the years, dynamic range was just always big. The so-called loudness wars were in effect. But in many types of music, we want quiet passages, loud passages, so classical music, jazz music, folk music, just maybe not heavy metal or things like that. So what can we do? Well, there is this thing called dither, and we'll see that in the next note set, and there's a cool historical story. So if you're interested to know how some nerdy engineer hung out with some rock stars of the 70s and 80s to make digital audio sound good, check out the next video. So I hope to see you there.